let's say we're given the following sequence. An equals 2n over n plus 4. Okay. And then we're supposed to, let's say the problem tells us to apply this to the following function, e to the 2x. Alright? So what we're asked to compute is limit as n goes to infinity of f of an, so f of the sequence. So we know that by the theorem that I just explained in the last slide, we can bring the function outside the limit, or we could bring, you could either say the function is brought out or the limit is brought in. It's the same concept. So like that, right? And then this equals f of L. So our main concern here is to find this limit, to find that L that we're going to plug in to the function. So let's get to it. So limit as n goes to infinity of an is equal to, I'm just going to replace this part now in for it. So then we get 2n over n plus 4, right? And then I'm going to divide by 1 over n on both top and bottom. Okay, so on top the n's cancel, and then on the bottom we're left with, well, okay, so we have a 2 on top, and then on the bottom these n over n is just 1 plus 4 over n, alright? And then we have, when we plug in infinity, we get 2 over 1 plus 4 over infinity, and this tends to 0, so that's going to go away. And our limit, so this is going to equal 2 over 1, which is just 2. Okay, so now this was the inside, right? The inside parentheses, this is our L. 2 equals capital L. So then we just have that f of L equals f of 2, right? So we're just going to plug in 2 for the x spot. So now we have e to the 2x, which is now e to the 2 times 2 equals e to the 4th. And that's our answer. Okay, that was pretty simple. Alright, so now on to the next topic. Now we have something called bounded sequences. So this kind of relates to limits as well. But okay, so there's two cases for bounded sequence. So the first is from above. So this just means, let's say you have some function, all right? So we have some function or going along, and then it's, I don't know, let's say it starts up here and then it goes down and whatever. So let's say it never goes above a certain y value. So this is y equals m, right? Because it stays at this constant capital M. So in this case, m is considered our, the term is upper bound because it's on top, right? So our sequence can't go above this value. Okay, so basically the formal definition says if there is a number capital M such that, this is an abbreviation, an, such that our sequence is always less than or equal to m. So it can touch this line, like let's say it starts there, or eventually it goes up to that line, but it can never go above that line, okay? And this is for all n terms, okay? And yeah, okay, so that's the first case. And then there's the second case. So this is from below. So this one's going to look like, let's say we have something here, and then we have some function or some sequence going along, and the values look like that. I don't know why they look like that, but let's just say it does. And they never go below a certain line. Now this is y equals little m. Okay, so this is little m is going to be called the lower bound. Okay, and similarly, this is if there is a number little m such that an is always greater than or equal to little m. So it just has to stay above this line, basically. That's the whole concept behind it. And this is, again, for all n. Okay? So, yeah. So for the first case, it's just saying that if there exists a big M such that the sequence always stays below it or is equal to it, then the sequence AN has an upper bound. And then similarly for the bottom one, then the sequence would have a lower bound, it's called. Okay, so now just to build off of that, let's say we have some sequence, and then the values go here to here to there, and then let's say it stays below the capital M that I was talking about, so this is our upper bound, and let's say it's always above a lower bound, little m. So then in this case, when it has both, when sequence AN has both upper and lower bounds, then it's said to be, and then this is a really original term, then it's said to be bounded. Okay, so that's pretty easy to remember. Anyways, and the most important part from this that I'm going to write is that if, and this might or might not be a theorem in your book, but anyways, if the sequence AN converges, so now we're looking at a limit kind of thing going on. So if it converges to a certain limit, right, let's say this one goes to some L as it goes along, right, so this is L, our limit. So if the sequence converges, then we know that AN, sequence AN, is bounded. Okay, so this is kind of just like common sense. I mean, if you start at a certain value, let's say, and then you're going along and it starts to tend toward a certain number or a value, this limit, then we know that there has to be an upper bound on it and there has to be a lower bound because it's kind of getting narrower and narrower, and it's not varying as much. Okay? All right. Now for another term I'm going to introduce is called monotonic. Okay, or monotonic? I think it's tonic. Monotonic. So, or tonic, whatever. Anyway, so this mono part, that means one. So I think of this as a term that means one way, okay? So there are kind of two ways that it can go, or two options, two cases. So the first would be when a sequence is increasing for all n. Okay, so increasing means that the following. So each AN term has to be greater than AN, oh wait, hold on, AN minus 1. So this means the term right before it. So let's say A2, our second term, has to be greater than the first term. All right. Okay. Yeah. So then pictorially, this would look like, let's say on a number line. We're living on a number line or something for some reason. Let's say our A1 starts here, and then the next term has to be to the right of it. It has to be greater than. So A2 is here, and then A3 is here, and then A4 is here. Basically, you can't backtrack. You can't go in the opposite direction. So increasing means you're moving right on the number line. Okay? And then on the other hand, decreasing, this is our second option for all n. So if our sequence is continually decreasing, that means that each term has to be less than the term before it. Okay? So on the other hand, this would just mean that, let's say A1 is here, then A2 has to be to the left of it somewhere. And then A3 has to be to the left of A2. So in this way, it's going left on the number line. Okay. So then, again, building off of this, we're going to explore a theorem. Okay, so the theorem now says, there are two parts to this. So the first deals with the increasing monotonic function, or sequence. So the first one is if our sequence, AN, is increasing I'm just going to abbreviate, increasing, and an is lower than, or less than or equal to big M. So this, remember, this is called an upper bound, right? This is what our sequence has to stay below or equal to. And then we have then we know that our sequence, an, converges, and the limit of it to which it converges must be, so limit of an must be less than or equal to m. Okay, so again, I'm going to revisit the number line. So let's say we have a1, a2, and we're going along, and then there's this upper bound here, m. So here's our big M, right? And as we're going along, our terms must stay to the left of this. So they're going to get kind of scrunched up toward the end here, and they're going to approach some limit, L, let's say, which could be to the left of M, but it can't be on this side. Okay, so L could be on the left of or right on M. Okay, and then on the other hand, if we have in the decreasing case, if our sequence is decreasing, is monotonic and decreasing, and an is greater than or equal to little m, so remember this is called the lower bound, this is what it cannot go below, then we also know that an converges, our sequence converges, and the limit in this case, as n goes to infinity, of an has to be greater than or equal to little m. So on the other hand, this one, let's say a1's here, and then a2, and we're going along to the left, right, because we said it's decreasing. But then we have a lower bound of little m. So then as we go along, our values are going to, they still have to keep moving left, but they're going to approach this m, this little m here. So our limit either has to be to the right of this m, or it has to be on it. It cannot go to the left of it, because that would be less than little m, which is not allowed because m is our lower bound. Okay? So that pretty much wraps it up for section 1.1. All right.